So 6.3, we're doing volumes of revolution again. Or revolving. And this is called the cylindrical shells method. So like, just for a quick example, without doing anything in there, the disk method, I don't know why I have hyphen in there. Let's say we had some shit like that, and this is one of the problems we did earlier. Our dx had the same letter as the axis of rotation. The washer method we still make a disc, or I'm not sorry, not washer, the cylindrical shells method. We are doing like, it's like a soup can, a cylinder that's hollow. But on this one, we're going to do it sideways. So like the cylinder is like this. If you watch the video on this, and so like, well, let me just emphasize, the cylinders go out this way. You get a larger cylinder, and it's like if you had a roll of toilet paper. Everybody knows what fucking toilet paper is. I fucking hope. If you grew up, well, if you grew up with a bidet your entire life, you may not. I don't know how it's possible. If you grew up with a bidet, you had to have gone on vacation sometime. Family's got some money. Like peeling off just the outer ring of paper and you made a little cylinder out of it. That's what a cylindrical shell is. And so this is like unraveling the whole fucking roll of toilet paper, one ring at a time. That would be working inwards. We can work inwards or we can work outwards, but you get a whole lot of shells. So like a full cylinder would be the area of this pi r squared times the height, but the shell is just the outer ring. The shell is the ring. And it turns out when we do this, the volume of the cylindrical shell, and if you want to see the derivation of it, it's in the little mini lecture video I made. It's on Canvas. This is 2 pi r times h. Times the dr, which is our thickness. I think the easiest way to remember this, what is 2 pi r? It's the circumference of a circle, right? It's exactly it. So you're making a circle, and then you're giving it some height. That's technically what a soup can is if you cut off the end, just like a metal pipe. There's a better example, pipe. Soup cans have tops and bottom. We don't really want that. But like a hollow pipe, it's got the same circumference the whole way. But since we're doing these shells and we're going from outward to inward, in this case, our D is in this direction. We would be going dy here. For the same shape, the same revolution, it gives us a way of tackling it with the other variable. Does that make sense? Because we're starting at the inner radius, like r equals 0, and we work out to the edge of it, r equals the function. But in this case, I don't want it a function of x. I'm going along y, so I want this to be a function of y. So let's do some examples. So the first example we're going to do is going to be y equals cosine of x squared. And we're going to use y equals 0, x equals 0 as some boundaries. And we'll do x equals the square root of pi divided by 2 as another boundary. And we will rotate around y. We can work with this as is, or we could do a substitution. Let's see, what's the best way to really go here? I'm gonna leave it as is. I think it's the harder way, which means you'll learn more from it. So how do I graph this? Well, x equals 0 and y equals 0 are my axes. So that's two of them. Let's say this is square root of pi over 2. And I know if I stick in x equals 0, y equals 1 is the top. If you're kind of curious, like what's going on here, how far does cosine go down? What's the y value when cosine is that value? Square root of pi over 2 squared. I get y equals cosine of pi over 4, which is root 2 over 2, which is about 0.7-ish. And we know cosine curves downwards as it's going this way. And this was a boundary. That looks like my region. If we spin it around y, we got some shit like this, where it kind of looks like we have a little cake with like a puffed top. So like puffed up a little bit. Kind of like a cake. Cakes puff up in the middle a little tiny bit. Little, just the tiniest bit. Interesting. I wonder if we could model a cake with cosine. Try to stick math into anything. If I could combine math and food. All right, let's do both methods here. So like if I were going to do the disk method, the disk method is doing like a tier of the cake. So disk method would give me a tier of the cake. And it looks like that thickness is a dy. If I do the shell, I'm literally doing like a circle like this, and we're going outward, and our radius is along x. So we're going to have dx. So if I do the disk method, like if I do a like if we look at the side profile of this, 0 and pi over 7, this function changes. Like our radius changes for the disk method. R here is fixed. R up here is not fixed. So doing the disk method, I need to go like from 0 up to square root of 2 over 2. Not 0.7, I want to use the actual value there. And remember, disk is doing like pi r squared. Well, that's not changing. R squared is just square root of pi over 2 squared dy. And then I need my radius up top from root 2 over 2 to 2 to 1. The radius here is x. Radius is x. So I need to solve this for x. So y equals cosine x squared. We'll do cosine inverse of y equals x squared. So x equals the square root of cosine inverse y. Ugh. That's got to get squared because that's my radius. That's my disk approach. Fun, right? First one's super easy. There we go. Good call. So this is like pi times pi. I've got pi squared over 4. I integrate dy, I get y, and we're going from 0 to root 2 over 2. Plus, as Dat was saying, this is just root 2 over 2 to 1 of pi cosine inverse y, because the radical and the square go away. So I got pi here. And if you pull this from a table, we get y cosine inverse y minus square root, square root of 1 minus y squared. Evaluated from y equals root 2 over 2 to 1. Ugh. Ugh. That's some serious ugh. Top part's not too bad. We get pi squared root 2 over 8 minus 0, of course. What do we get on this bastard? So if I stick in 1, I've got 1 cosine inverse of 1. So this is like cosine of theta equals 1. Where is that true? What's theta got to be equal to get cosine equal to 1? 0. That ends up being 0. Well, that's handy. Minus square root of 1 minus 1 squared. That's also 0. And then we do the square root of 2 over 2, 1. That's at pi over 4, right? Minus square root of 1 minus square root of 2 over 2 squared. Which is like 1 minus 2 over 4. Which is 1/2. That's the, so I got this minus square root of 1/2. And this was all 0 here. So I'll just put the pi over it. We got, and that if we put it all together, pi squared root 2 over 8 plus, well, minus pi times this shit right here. Pi root 2 over 8. Square root of 1/2 is root 2 over 2. And it looks like this filthy bastard cancels this one. And all we're left with is pi root 2 over 2. Ugh. That was doing the disk method. There's no way in hell you're going to remember all the tables of integrals. Remembering the inverse trig functions, yeah. This isn't even worth taking the time to derive. You can, using something we haven't covered yet. Integration by parts comes up later. But you can come up with this being the integral of cosine inverse y. I don't think we're going to do it. It's a pain in the ass to do. So at some point, you're just going to go table for the thing. That was the disk and washer method. Let's see what we get with the cylindrical shell method. So the shell method, we're having hollow shells like that. So our dr is in the direction of dx. And remember, this had volume equals 2 pi r h and then dr. So we're doing it in terms of dx. It looks like we're going to go from 0 to square root of pi over 2. We're gonna have 2 pi. If we look at the big cake that we had. R at any given ring. This R right here is just X. And my height is the vertical height. This actually goes all the way up to the top of the cake. The height equals the top of the cake, which is Y. And Y was cosine X squared. That's my height. That's my R. And we're doing dx. Does that make sense looking at the picture?
Y equals height.
Y equals height, because it's going all the way up to the top. So the height is that. So it's going up to the line that we had, the Y equals cosine X squared. But I don't want it in terms of Y, I want it in terms of X, so we can just use the function as is. So this toilet paper roll is growing shorter as we go outward. Which toilet paper rolls don't do, but I think you still get the idea of like a paper ring going. Paper is super thin, so you can get like the infinitely thin shell going on. We're just going outwards. Does it make sense? Everyone good with that? Well, fuck working with that. Let's do a U sub. So I have my 2 there, I have my X there, and I have my dx there. I am going to redo my limits. When X equals square root of pi over 2, U equals that squared, which is pi over 4. So my upper limit will be pi over 4 now. My lower limit is still 0. And all I have left, the 2x got eaten up doing my U substitution. All I have left is a pi cosine of U du. You'll find with practice that if the thing inside like a weird function like cosine or exponential is just like a number times x, you can easily do the integral and divide by the number. But like anything else, you're better off doing a U sub because you're not doing that shit in your head. Yeah.
Whatever the 2x or the 2 and the 2x dx. So the x cancels out. What is it?
So I could rewrite this. I'm just going to reorganize it real quick. Pi times cosine x squared. And then I'm going to put the 2x with the dx. So I kind of changed the order of everything. Does that make sense? There's my 2 and there's my x. I just moved them to the end.
Okay.
And now this was my du.
Okay.
If you don't like doing that, you can also do this is dx equals 1 over 2x du. Stick in the du and you'll see the 2x cancels there. You guys with me on that? I bet you guys, how many of you guys did any calculus over summer? Couple of you. Good, that's like well, did you take Calc 1 over the summer? That would be why. Although some people took it in spring and like if you took up the entire summer and didn't do any of this shit, your calculus skills are rusty. But we'll get them back up to speed. This is an easy integral, right? It's just sine. So I have pi of sine of pi over 4 minus sine of 0. Sine of 0 is just 0. Pi over 4 is √2 over 2. And isn't that what we had left with the disk and washer method? But this was a shitload easier. Simple, easy use of. Simple substitution. This one, I had to use a fucking table of integrals. Like you can Google table of integrals and just scroll and search for what you're looking for. I promise you on any test, you're not going to need anything from a table of integrals. And if you did, I would give it to you. I would just say this integrates to this. That's actually helpful for you. You're like, fuck, I know I'm going to need that. This better show up somewhere. All right, you guys ready for another? Let's do y equals x cubed. Y equals 1. X equals 0. And we're going to rotate around y equals 1. So if we do a sketch here, like y equals x cubed does some shit like this. Y equals 1 is there. X equals 0 is here. So this is our region. And we're going to rotate it around y equals 1. So it should go up like this. So disk method. We would have a disk slice like this, which means we have a dx. And like, what's the radius? Well, the height of this thing looks like 1 minus x cubed. That's one way of looking at it. The other way of looking at it is do the y value minus the axis of rotation. So doing y minus 1 or getting x cubed minus 1. Now, either way, it doesn't matter because remember, we're doing pi r squared. So squaring it gets rid of the negative sign matter. Either way, when you do this, you're going from 0 to 1. One minus x cubed squared. I got a pi, I'll put it out front, dx. So 0 to 1, what do we get when we expand that? So we're gonna get pi times 1 minus 1/2 plus 1/7 minus a bunch of zeros. This is pi times, we got 14 over 14 minus 7 over 14 plus 2 over 14. 9 pi over 14. This method was pretty easy. Let's do the shell method though. Shell, we're doing some rings like this. And so now on the shell method, we're doing dy. So remember, our volume is going to be 2 pi RH dr. In this case, we've got 2 pi. I don't know what R is yet. I don't know what H is yet, but I've got a dy. So my R here looks like the R I had here, but I don't want in terms of X. I want in terms of Y. R looks like 1 minus Y. The higher minus the lower. This has a value of Y right here. And this has a height of 1 right here. So subtracting them, I get 1 minus Y. Does that make sense? My height is going this direction. So my height is like in terms of X. So I want to rewrite Y equals X cubed in terms of X. X equals cube root of Y, or Y to the 1/3 is probably the easier one to do. That's my height. And we're going from 0 to 1 because that was our region. So we've got 2 pi 1 minus y times y to the 1/3 dy. This actually isn't too bad here. You distribute. I'm gonna pull the 2 pi out. I've got y to the 1/3 minus y to the 4/3. So if I integrate, it goes up a power, so I'm making this go up to 4/3, which means I put a 3/4 in front. And this one is going up to 7/3, so put a 3/7 in front. We're doing y equals 0 to y equals 1. I've got 3/4 minus 3/7 minus 0 minus 0. So if I get a common denominator, the common denominator is 28, 4 times 7. This is 3 times 7 minus 3 times 4. (21) minus 12 over 28. I'm going to use this 2 to simplify this down to 14. And I'm left with pi times 9 over 14, or 9 pi over 14, which is what we had up here. As we saw in the last problem, sometimes one method works a lot better than the other. The disk method sucked on the last problem. Shell method worked great. Sometimes it's the other way around. The disk method works great. The shell method sucks. We won't integrate this next problem, but I want to do the setup for both. Does anyone have any questions on this? Or if we have time, we'll find the solution. You guys ready?
So you recommend that if we get stuck in one method to move to the other one?
I strongly recommend you try to look at what write up the integral one way. If it's easy to solve, just do it. Don't bother with the other way. If it's not easy to do, look at what the integral looks like in the other way before you settle on doing the hard one. Does that make sense? If it's already something you know how to do, even if it takes like a U sub isn't that bad. I would go ahead and do it, but one of those, we had like an inverse trig function and you're like, no. That's a hard pass. So on this one, we'll do y equals sine inverse x. Or x equals sine y, same thing. Same. We will do this from 0 is less than or equal to y less than pi over 2. We will also use y equals 0 as a boundary. And we're going to rotate around y. Now, I don't remember what the shape of it looks like. I really don't. But I know I'm going from 0 to pi over 2. So what are my two x values if I do that? Y equals here, y equals pi over 2 here. I know this is one of my boundaries. That's a boundary. If I stick in y equals 0, then x equals sine of 0 is 0. So I'll have a point there. And if I stick in pi over 2, I get x equals 1. Now, I don't remember if it curves like this or if it curves like that. I don't think it really matters at this point. I'm going to do it like this. That is y equals sine inverse x. And so it looks like this is the region we're doing. And if we rotate that around y, okay, so my disk method is doing some shit like this. Disk, it's going to have a thickness in dy. And it's not even a disk, it's a washer because we have a hollow spot. Washer method. So we do like pi outer squared minus inner squared. And we're doing in terms of dy. Why do I have that? That doesn't even work. The fuck did I do? The outer radius in terms of y looks like y. No, it's just 1. The outer radius is 1. That makes sense. And the inner radius is, we want in terms of y. So sine squared y. So our washer method setup is giving us from 0 to pi over 2 pi times 1 minus sine squared y dy. Okay. Our shell method is doing some shit like this. That's like the side of the can, and we're circling like this. So the shell method is using a dx. So we're going to have 2 pi RH dx. It looks like we're going from 0 to 1. We have 2 pi. R is x. Our radius is just x. And our height is y. At any given point, the height of that cylindrical shell is y. But I want it in terms of x, which means I have a sine inverse x here. So those are our two different methods. One of these is a lot easier to do than the other. going off of cosine squared y plus sine squared y equals 1. This is just 0 to pi over 2 of pi cosine squared y dy. This is easier than the other stuff, assuming you remember your trig functions. We saw one of the variants of cosine 2 theta was 2 cosine squared theta minus 1. So if I solve for cosine squared, I can get something where I don't have a square anymore. I'll add 1 to both sides. And then we'll divide by 2. And we'll see that cosine squared theta, or if I say cosine squared y, that should equal 1/2 times 1 plus cosine of 2y. So I'm going to make that sub. I still have my pi. Then I've got times 1/2 1 plus cosine 2y dy. Are we having fun yet? You may wonder why the fuck rotate around an axis? If you've played around with like AutoCAD or any of the engineering shit, we do a lot of stuff that's got a weird shape that is literally made by rotating it around something. It happens a lot. All right, so I got a pi over 2. I can pull that out. I'm just looking at it real quick. What do I got? So pi over 2, we integrate the 1, we get a y. We just did this earlier. When you have a multiplier times what's inside, it's easier to just integrate like the multiplier is not there, but then divide by it. And we're going from y equals 0 to y equals pi over 2. So I have pi over 2 plus 1/2 sine. If I stick in pi over 2, multiply it by 2, I get pi there. Minus 0 plus 1/2 sine 0. Well, that's 0, that's 0, that's 0. And all I'm left with is pi over 2 times pi over 2. I've got pi squared over 4. And that's the example of the kind of work I would expect to see something like this. I probably would have just stopped with the washer method myself. It's knowing, seeing a sine inverse, knowing if I don't have it here, it's going to be in the other one. And fuck that. You'll find if you do the sine inverse one, there is a table of integral thing for x sine inverse x. Or it'll say u sine inverse u. There is a formula for it. And when you go through it, you're going to get pi squared over 4, but it's just ugly as fuck. Here we didn't need a table. All you had to do is remember some tricks. That's it. That's all I got for you. Do we have fun? I don't know if it's fun, but it's like, it's doable. Does serve a purpose. Shows up, this kind of shit shows up a lot in engineering. I will see you guys on Wednesday. Have a good day.